Hello, everyone. In this video, I'm going to demonstrate the PC update unit in my Logisim circuit. Let's get started. So this is the y86 sequential processor that I designed and I'm implemented. And here it's almost same with previous tutorial demonstration. But here we have one more small module, which is condition module here. So previously we didn't have this and it's not connected with PC update unit. And also PC update unit didn't take all the three possible candidate value of next PC. But now I made all the connection. So here the rightmost is what? Okay, sorry, let me zoom in a little bit so then you see the signals here. Okay, so this is the input to val P, and next this one maybe input to val M, maybe this one is the input to val C, and this is the input condition signal, and this is the input to I code, and then finally it will select correct next PC value among val C, val M, val P, and through this new PC line. Okay. So before we we need a test program. Okay, let me show you my test program. Since we have a complete PC update stage, we should test jump instruction. Now we can test jump instruction. All right. And I'm using the example that I have used in the lab 5. Okay, so which is just a summation. This program sum all the elements in the array here, so ARR array, and yeah. So the value, the output value, then it prints the count value and sum. Maybe count will be 0 because it count down from 10 to 0, and some value will be 55. Okay. So it's not typical loop program, the program with loop, but I intentionally make this loop with this loop using go to statement with label. Okay, so if we use for loop, then it will be super simple, like in the one line. It's really simple. Like, okay, we are done. But since we need to write assembly program of this C program, so assembly doesn't have this rich program struct. It has only jump instruction, and we can specify a specific address using label. So that's why I used go to statement and loop label in the C program. Then we can easily convert C program to the assembly code. Okay. On the right hand side, we have a we have a assembly program. The same thing with C program on the left hand side. Here, I just manually make a label for the first part as a main label, main function, and then it follows through this loop, and then finally stop and at the end label. Okay, so it actually it does same thing. You can refer to this assembly code for your test. And here at the last part, we have a data. So that the array actually stores in the is stored in the memory, and the start address is labeled with ARR. And then we have a 4-byte long data, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So then you can make this, you can run this, you can compile this program to generate binary file. And then you can convert that binary file for the logic. Then you have two memory files, one for instruction memory, which stores machine codes, and the other for data memory, which stores data. Okay. I demonstrated how to convert binary file of y86 to the memory file for logisim in the previous demonstration, maybe the execution stage, sorry, data memory stage. So you can refer to that video if you don't know how to convert a binary file to the memory file for logisim. Okay. Here, let me quickly just run. Let's just read that out. The compile C program, and then run it. Okay. It prints, yeah, count value 0, sum value 55. It's correct, and this should be happening in the y86 processor as well, right? So let's first run y86 tool to make binary file. Okay, then we have a binary file. Then let's just run that binary file using y86, which is simulator of y86, and it outputs the values which changes during the run. Okay, so let's see, register values are changed. 3 register values are changed. That's true. And I used EAX for array address, and then EDX for what? I think this is for temporary value, and EBX for what? Some value. Okay, so hexa number 37 is 55 in this decimal number, so output is stored in 37. But count value is actually used what's that? ECX register, but since it initial value was 0, but after program finishes, the initial value was 0, and then I assigned 10 and then count down to the 0. So then it is not changed anymore. So only 3 registers are changed, and there's no memory changes because this program just reads data from the memory, no write to the memory. Okay. So the reason why I'm showing this, so when you actually finally demonstrate your program, you must show me the expected output or expected changes of your processor states, something like this output. Okay, you should show that before you actually run your logic. Okay, I'm going to talk about how to demonstrate, how to write up your report in the next video or next lab. So don't worry about it. I'm just roughly show you how to demonstrate in this video. But I'm going to make another video to demonstrate about demonstration of your term project. Anyway, yeah. Okay, so it seems the assembly looks fine, and we have expected changes in the processor. Okay, so I'm going to compare this value and the values or changes in the logic circuit. That's how I verify this program. And here, I'm not going to step through each cycle anymore, because I verified condition module separately, and then new PC PC update module separately, because it is simple logic. So I'm not going to show you detailed step-by-step changes. Instead, I'm just run. I just run. Enable ticks with very high frequency, maybe 2 kilohertz, and then wait until this machine get into the halt state. Okay, what is the halt state? When this instruction start executing halt instruction, that it cannot move to another instruction. Okay, then we will see I code is always 0 after some time. Then we know, okay, this processor fall into the halt state. Then I'm going to stop ticking and then see the results, like in the register files and the memory. Okay. All right. Okay. Give me a second. Let me load these two memory files. So note that once you load memory file to the ROM and save it, then it never cleared out unless you do it. But data memory or RAM actually is headache. So when you reset simulation, then the RAM is also cleared out. So you have to reload your data memory file to the RAM every time you reset the program, reset the simulation, this simulation. Okay. Okay, I loaded both instruction memory and data memory of the program that I showed you before. Okay, it's ready to run. Maybe we can see around this fetch unit, because we are going to see the I code changes and then we will stop it when I code keep showing 0. Okay, so frequency is 2 kHz. Okay, let's enable text. Okay, now it's brrr. Okay, let's wait. So I code is keep changing now. Okay, it does something. Okay. It takes time. It's not so fast, but it's okay as long as it runs. Okay, it's 0 now, and it doesn't change anything. Then we can stop. And then let's see the register file. So we know data memory is not gonna change, but register file it will be changed. Okay, how do I see? Okay, yeah, I don't want to show my inside module, but yeah, actually I already changed before I record this video. So in this case, what registers we need to check? We need to check, where is it? Yeah, register EAX, EDX, and EBX. So if you have a same values like 55, 1, and 37 in each these registers, then you are fine. And I will consider your processor works perfectly. Okay. All right. Yeah, this is it. And in the next video, I'm going to, like I mentioned, instruct how to demo your TOM project, entire TOM project, and how to write, what to submit. Actually, you may not have, you don't have to write anything more after you finish your implementation, because I'm going to ask you to submit whatever you have made during the implementation. Okay, if you follow my tutorial, then you may have some small sketches or small tables, then that is good enough. Or also you may have some test programs, then that is good enough. Okay, that's it, and see you in the next lab. Bye bye.